Hi everyone, today we're going to do the radioactivity lab. So the first thing that we're going to do is we're going to look at our Geiger counter, and this is going to detect any other radioactivity that we see. So the first thing you're going to see is that on the dial we have several different scales. So I set this on the 500, so we're going to read the 500 scale on here. And you can hear that ticking noise in the background. That's the detector collecting radioactivity. So there's no radioactive sample over there right now. So there is just background radiation. So what my assistant is going to do is he is going to do 2 separate 30-second intervals, and he's going to use the clicker, and he's going to use the tally counter, and he's going to click it every time he hears one of those disintegrations on the speaker. So he's going to go ahead and do that, and that's going to be part of the data that you'll have for Hi everyone, so we're going to continue with our radioactivity lab today, and so I have this setting on the lowest one, which is 500. And the background setting was somewhere between 17 and 23 clicks in 30 seconds. So one of the things I want to show you first is a piece of glassware called Fiestaware. And Fiestaware was made starting in 1936. And it had this special characteristic that this piece of glassware, which was actually flatware that you used to eat your dinner off of, it was coated with a uranium orange paint. This is uranium oxide. So what we're going to see, the first thing I'm going to do is bring the Geiger counter close to the plate, but then it's going to be so many clicks, I'm going to have to change the dial. So just raw on this 500, you can hear the background clicks. So the radioactivity coming off of this plate is so high that it's pegged. So if I do it at 500, it finally starts to come down, or sorry, 50,000. So it finally starts to come down to somewhere that I can see it on the meter. So one of the things that we're going to learn today is the particles that are being evolved from this plate are called alpha particles. And the alpha particles can be blocked by a source like a piece of lead or something even as simple as a piece of paper. So I'm going to show you what it looks like when I put in a piece of lead between the plate and the Geiger counter. So now there is so few counts coming through that we can even go down to the 500 scale, and there's somewhere between 50 and 100 counts coming through. So all I did was put a source of lead in the way to trap those alpha particles. So the lead foil that I have the paper that have the plate wrapped in helps prevent it also. So not quite as good as this piece of lead. So about 300, between 200 and 300 volts worth of radioactivity alpha particles. So what we have for today is we have a variety of sources of radioactivity. And so the sources of radioactivity we have today are Strontium 90, we have Polonium 210, and we have Cobalt 60. And so the next video is going to talk about how we're going to collect the radiation as we expose these samples to our Geiger counter. Okay, everybody, we're ready to start collecting the data on our first source of radioactivity. So the first source is going to be polonium, and it's polonium 210. So what we're going to do is I'm going to put it on the little tray, and I'm going to put it so that the polonium side is facing up. And I'm going to put it on the second tray from the bottom, or maybe the third tray from the bottom. Let's see how that one works. Okay, perfect. So now we should start to hear that there's more radioactivity being collected by our Geiger counter. So we're going to use our counter, and we're going to count for 50 seconds. So I'm going to put the timer on for 50 seconds, and then I'm going to start collecting. That was the end of our 50 seconds. So as you do this, I want you to count how much, how many ticks that you heard during that time as well. So the next thing we're going to do is we're going to leave that in, and we're going to put some sort of shield in between our source of radioactivity and our Geiger counter. So the first one that we're going to do is a piece of this one is polyethylene, and it says that this polyethylene is 0.250 milligrams per centimeter squared. No, 610 milligrams per centimeter squared. So we're going to see what the ability of this polyethylene is to stop the alpha particles. So we're going to do the same thing again. We're going to put our shield in. We're going to set our timer for 50 seconds and see what we get this time. Okay. Ready to start again. Okay, that's the end of our 50 seconds. So I'm gonna get the next source set up. Okay, so our next object that we're going to shield our radioactivity with is a little piece of aluminum foil. And this one is labeled aluminum foil number 2. And so on here, the number 2 is 3 milligrams per centimeter squared is the thickness of this aluminum foil. So we're gonna do the same thing. We're gonna put it for 50 seconds and we're going to see what the shielding is with just a layer of aluminum foil. Okay, all right, so I'm gonna get my counter started. Okay, so that was the end of our 50 seconds. So we have a whole variety of other things that we can do in here as well. We have different thicknesses of metal sheeting. We also have all the way up to some of these thicker pieces of aluminum. So we're gonna do this number 22 next. So the number 22 has a thickness of 12.9 milligrams per centimeter squared as its thickness. So let's do that one. So we're gonna take this one out, put that one in. And now we're gonna start our 50 seconds. Okay, that's the end of our 50 seconds for that one. So I'm gonna look around and find one more source of shielding, and then I'm gonna come back and we will do another 50 seconds. Okay, so we're ready to do another set of shielding. So we still have our source of polonium down below. And we're going to this time use the lead shield labeled E, and E is going to have 7140.3 milligrams per centimeter squared. So again, let's do 50 seconds on this one, and let's see what our count is. Okay, ready? Go. Okay, that was the end of our 50 seconds for that one. So the next thing I'm going to do is switch over and pick another one of the radioactive sources that we have. Okay, so our next sample is going to be Cobalt 60, but you can tell by the amount of radioactivity that's coming out of that Cobalt 60 that it's going to be a little bit too hard for us to sit and use our tally counter. So what we're going to do is we're going to use a program called Science Journal. And Science Journal has the ability to test a bunch of physical properties. So one of the physical properties it can test is sound intensity. So what I'm going to do is I'm going to record for 50 seconds the ticks that are coming out of that speaker. And then I'm going to put the lead sample in, and then we're going to look at it again. So we're not going to actually sit and count these ticks, but we're just going to be able to at least hear the change in the amount of signals that come out that speaker. So we're going to go ahead and hit start. And the pink box is the part of Science Journal that's it's recording. So if they were a little bit slower, we could actually sit and count each of the signals that's coming out the speaker, but it's just a little bit too fast for us to do that. So that was actually a nice little section right there. We almost could have gotten the count in that little window. So I'm gonna stop the video at 50 seconds, and then I'm gonna put in that lead sample, and we're gonna do it again. Okay, that's done at 50. Okay, so here is our signal, and I'm gonna save that, and then I'll screenshot it so we can all look at that. And then, so now let's go ahead and let's go ahead and do it again with our lead so that we can start our 50 seconds over again. So now it's a little bit slower, and actually it's pretty dramatically slower, where we could almost sit and count each one of those signals. Okay, so we know that this lead, this is the one that's labeled E, is much, much thicker, and it's actually a very good shielder of this sample of Cobalt 60. So the last source of radioactivity I have today is Strontium 90. And so we're not going to be able to test the counts on that because the counts are so high. You can hear that. But we are going to put a few shields in there to see what happens. So this is Strontium 90, and now let's put that lead shield in. Pretty dramatic. So this one we could actually use our science journal and actually get the number of ticks that are coming through after we have our lead shield. So that was the lead shield that is the thickest of all of them. Let's go try a little bit of plastic. Let's try a thinner one. So this is labeled lead shield A, and this is 926. So this is about, that first lead one was about 8 times thicker than this one. So the lead is good. Even this little bit thinner layer of lead is good. Let's go try some aluminum foil. So let's try number 9. So number 9 is labeled as 135. So you can hear that that one is not a good shielder of that radioactivity at all. So this thin layer of aluminum foil at 135 milligrams per centimeter squared, that is not a very good source to shield the radioactivity that's coming out of this Strontium 90. So Strontium 90 is in the same group as calcium. So patients would be given Strontium 90 and it would incorporate into their bones and replace some of the calcium, and then you can use that radioactive source as an imaging. So you can radioactively see the image of patients' bones. So Strontium 90 is one of those biologically relevant radioactive sources, along with Cobalt 60, and there's a couple different radioactive xenon versions that are helpful for medical uses as well. Okay, so that is the end of the data collection for this part of the lab. And so I'm gonna just have you continue on and do the post-lab questions based on these videos.